Okay, and now we're recording, and I think that we are live. Let's see. Yes. Now we're recording, and I think that we are live. Let's see. My 3D printer is currently running. I'm printing something from a hydroponic system. It's the end caps to the hydroponic reservoir. And here, I'll show you in a minute. My 3D printer is currently running. I'm printing something from a hydroponic system. Okay, yeah, we're live and everything sounds good. I'm gonna go to YouTube and check that out as well. Let's see. And I'm live on YouTube as well. Beautiful. All right, fantastic. What's up? What's up? Okay, so today I'm going to be looking into electrolysis reactors. I'm going to be designing one for myself here. For what reason? For what reason? The reason for future experiments. You know, I want hydrogen, I want oxygen to a high level of purity. And so from there we can begin to study other systems. I'm not sure. I mean, I don't really have an end goal other than I want to create technologies for the benefit of humanity. So this is the reason we're here. I want to give power to the people in the sense of self-sovereignty, you know, where people are able to provide for themselves without having to rely on a larger power at hand. I don't know. That's what I foresee for the future, and that's a beautiful way of living. So this is my reason for studying physics, for studying engineering. I want to invent, and I want to always invent with that in mind. Power to the people and self-sovereignty. Okay, so this is my hydroponic system. Holy smokes. It's all white for my PLA filament because I 3D printed it, and wow, it's incredibly hard to see, is it not? Alright, fine. Let me just turn down the exposure of my camera one time. Oh, yes, I forgot. Okay, you can't see my screen either, so boom, here we are. I'm just in the whiteboard. Okay, actually, I'll make this big one more time so that I can show you this, and then I'm going to edit the exposure and turn it down some. One more time. Surely that'll help. Okay. Alright, so let's take a look at this again. Here's my hydroponic system thus far. Right here you have the pot itself, in which you will put your seedling after germination has completed. You drop your seedling down in here. This is the reservoir, and right now I have the end caps being printed. This is the bubbler here, this pipe here, where I'll add the air compressor so that we don't have stagnant water, and we can keep things in motion and moving. I think it's necessary for the process. If I build when I do build larger systems, I'll probably introduce a water pump rather than an air compressor because I think it'll be more efficient at that point. Here's the bubblers, there's the holes. Again, all 3D printed. I wanted to do a normal elbow, but I use Blender software to do my 3D prints, and quite frankly, I can't get a 90-degree elbow, or at least I don't know how to. So in due time, you know, I'll eventually figure it out, but for now, that's just what I did. And it should work out well. There's no reason to have the perfect 90-degree elbow. I just needed 90 degrees, and that's beautiful. So this is where our design has come to thus far. Just waiting for the end caps. But it's nice. One of the end caps, too, I left a space to where I'm going to put plexiglass inside of it, so that you'll be able to see the progression of the plant growth. And so it's going to be a beautiful thing. It's going to be really beautiful. And then on the other side of the end cap, all into one 3D print, right? It's just one print. I have an inlet and an outlet to add water and to get rid of the water that's already in there. Because I'm not sure what the process of consumption of the minerals in the water is gonna be like. Like, is gonna turn the water dirty? Am I going to want to replace the water eventually? But these are all things to think of when building the hydroponic system. You know, I wanted to build it so that it's the easiest process for people to grow their own food. I don't want it to be a strenuous or tedious process. I want it to be simple and straight to the point. And I want the system, to be doing most of the work itself. So, you know, I'll automate the watering, I'll automate the lighting, I'll do whatever I need to automate this process. You know, even go as far as to automate the harvest. Because why not? Why not? What a beautiful thing to have a completely automated gardening system in your home. So these are the ideas with the whole hydroponic system. But today I'm going to be designing an electrolysis reactor. And as I said in the beginning of the video, the reason for this is because I want to do future experiments and I want to look into, I don't know, just hydrogen as an element. You know, it's the first element on the periodic table. It's the lightest element. It only consists of one proton. So it's a good place to study the elements, right? All for scientific pursuit. So cool. What I'm going to do first is I have this whiteboard here. Oh yeah, here, let me switch now. So I have the whiteboard in front of me here, and I'm going to be designing on paper first. And then I will go into my Blender software and start 3D designing for my printer. And then from the Blender software, we'll export the file and import it into the Creality slicing software. And then we'll slice it, it'll render the G code for my 3D printer, and then we'll print it. And actually, I've had a horrendous experience trying to get my 3D printer to work properly. And I figured that higher heat is the solution. Higher heat is the solution, at least for my issue. I wasn't getting good prints consistently. Only every now and then I'd get something good, and I couldn't traverse the full area of my bed because for whatever reason I have like inconsistencies in my leveling, in my bed leveling. So excuse me. So higher heat solved my problems, and now I'm getting good consistent prints, and it's beautiful, it's amazing, and I can traverse my entire bed now and no problem. Like right now I'm printing the largest piece. Well, it's 3 pieces, and that's why it's taking up such a great area of the bed. But this is the first time that I've expanded to such areas of the bed, and it's coming out nicely. So hip, hooray! It's great. Let's go. What's up? I'm trying to see how many people are in here. Yo, what's up? What's good? Comment how you're feeling. Are you going to be celebrating Halloween? Oh, Halloween. Okay, Christ is King. Do not ever forget it. So, alright, so here we are. Let's get into the design. So now I already have somewhat of an idea how I want this to look. So let's see. Again, I'm on my Intuos pad and I'm drawing on the computer. Like, it's probably not going to look great. I'm much better freehand on paper. But this is a bit of a task here. And I got 2 screens going, so it's rendering to both screens rather than just the one. So now I'm only drawing on one side of the Intuos pad. It feels even more awkward. Okay, it's not bad though. Okay, so it's gonna be like this. We're gonna have our outlet here. For the hydrogen in this section, this will be the section that produces hydrogen. My electrodes will come in here. Just like this. Okay, so these are my electrodes here, and these are going to be the positive ends. And then what I want to do is, there's going to be a wall here. I'm trying my hardest to get a good picture. Okay, so there's gonna be a wall here. And that's there. And the thing about this is I want these to be as close as possible. I want the positive, which these are gonna be the positive electrodes. And they're gonna be sectioned off into their own area because they're gonna be producing hydrogen gas, which is gonna flow in this direction through the outlet. H2 gas. Okay, so this is what we're gonna be producing, and this is the positive end. And so now, you know, okay, so there's some different things going on here. The rate of production of hydrogen and oxygen is going to be dependent upon the amount of current that we have. The amount of current, because the current is like the physical thing which is imparting electrons onto the system. And so that's how our reaction is occurring, by the transfer of electrons. So, with that being said, there's a few things that determine our currents. It's going to be the resistance of the salt water, or, well, resistance of whatever the aqueous solution is. And it's going to be the amount of the voltage, because according to Ohm's law, the voltage, here, let's look at this. According to Ohm's law, let's make sure you can see this too. Voltage divided by resistance equals current. Okay, and that's Ohm's law. So it's a very simple algebraic equation. So these are the two things. Our voltage now, our voltage is going to be determined by the by the magnitude of the electric field and the distance between the electrodes. Well, the electric field is kind of like related to the distance, so I don't know, I just want to make sure I'm wording this correctly and that I'm true in everything I'm saying. Anyways, the voltage is dependent upon the electric field, and the electric field is dependent upon the distance between the two electrodes, the positive and the negative. So I want this wall here to separate the waters, but still to allow the electric field to propagate. So it's going to be made of the 3D printing, or the PLA filament, and I don't know what any capacitive properties or dielectric properties there are to this PLA filament. I could look that up and I could add it into my calculations if I want to get that detailed, and perhaps I will, but as of now, I think I'm just going to design it and say fuck it. So there's that. Okay, so there's our positive electrodes. I'm going to have our negative electrodes coming in from the side like this. And mind you, this is going to be all around. So I'm only conveying or depicting 1, 2, 3, 4 electrodes, but really it's going to be like 1, 2, 3, 4, 5, 6, 7, 8, like all around the whole circumference of this circle. So, okay, that's where the hydrogen is going to go. Okay, these are my negatives. Negatives. I don't know, I almost want to get rid of that, but okay, there's that. That's going to be some sort of placeholder for the electrode, and then obviously we're going to have our wires running. Those will be connected, these will be connected. And essentially everything's going to be in parallel. It'll be in parallel is what it will be. So we can draw out this circuit too when the time comes, but for now I'm just going to figure the geometry of my setup. So now there's this. And what I can do here, you know, just for looks, because I mean you still want it to look nice, you want some aesthetic quality to it. In addition, okay, so you want high engineering efficiency, high rate of production of hydrogen with least amount of with the least amount of watts. Highest rate of production of hydrogen with the least amount of watts. So along with the quality of efficiency, we also want the quality of aesthetics. We want it to look nice, okay? So that's what I'm trying to say here. And these are the things that like Elon Musk has presented to the engineering industry. He's really bringing back aesthetics. You know, a lot of things we see around us in like cities especially is the very dystopian and uniformity of like skyscrapers in like this modern era. You know, things like this. I don't know. I don't like to see it. I don't like to see it. You know, we want things that are inspiring, that are inspirational, things that motivate us to do better because of how awe-striking it is. We look at it and it's so beautiful that we're inspired to take action ourselves and produce something. You know, those are the things that we want. And I'm pretty sure, like, not like you couldn't argue otherwise that Elon Musk is like very inspirational, you know. So let me not, like, what's that word? Let me not fucking I'm trying not to curse either, but let me not glaze him too hard, right? But it's something that he's presented to engineering again is inspiration, and he's not the only one. There's plenty of inspirational companies. You know, or what is it? Atlas, like the robotics company. Or that's their Atlas robot, and the company is Boston Dynamics. For whatever reason, seeing robots like is genuinely inspirational. That really makes you feel like the future is approaching. And you know how beautiful and how hopeful to witness the future approaching. It gives me hope in a rather destructive world. We see a lot of destruction around us. Okay, so I'm just gonna put the walls like right here. I don't really know. I guess I don't want to interfere with that at all because I want it to be. Man, it was really off. But anyways, okay, so this is gonna be the reservoir, but also so the main reservoir, but also the wait a second. I have this backwards. I don't want these to be positive. I don't want these to be positive if this is where the hydrogen is going to be produced. Because remember, hydrogen ions are positively charged, so they're going to be attracted to the negative. And oxygen ions are negatively charged and will be attracted to the positive. So let me just flip these around. Because I want my hydrogen to be produced in the main chamber and my oxygen to be produced on the outer chamber. And now from here, so I'm just thinking about what I can do here. I think I'm just going to, you know, I want to keep my volume as small as possible too, because with a small volume, I'll be able to see a small production of gas. If I have a great amount of volume, I'm not going to be able to notice the changes so easily. And this is something I experienced with my first build. You know, it was too great of a volume and I produced way too little hydrogen that I did not notice my production whatsoever other than the bubbles at the electrode. And so, because there's a couple things I'm going to add to this system as well. It's not going to be just the reactor. It's going to be a bubbler. And from the bubbler, that's where I'll take the hydrogen. Maybe the bubbler and then a filter to filter out any oxidizers or anything such as this, because I want no other gases in my hydrogen. I want it to be pure hydrogen. Which I hope nothing that I'm explaining right now is like, nah, I mean, this is common knowledge, you know? There's something you can look up. But anyways, we gotta keep the volume small, but that's doable with my 3D printer. I can scale it to any size that I wish to. You know, obviously with limitations. But so this is where we're gonna go, and then I think I'm gonna run several pipes from this point. I don't want those. I'll just go like this. So there's this section, and then he'll come up like, okay, this is an awful drawing. I'm just trying to get an idea of what I want to do. Okay, so, like this, we'll keep this here. We'll continue to proceed with this, even though it looks like garbage. It's like a cartoon drawing. I don't like it. But here we go. Something as simple as this. And then these will be the pipes that will carry the oxygen to its destination. Its desired destination. This will be the pathway for the oxygen to flow. O2. O2. H2. Okay, we have our negative electrodes here, and this is where the hydrogen will be produced. And then we have our positive electrodes here, and this will be the oxygen is produced. Now down here, the solution will consist of, I'm trying to refrain from using salt, sodium chloride. So we have some options here, and this is my reservoir. Reservoir. Oh wait. Reservoir. There, I think I spelled that right. Reservoir. We'll call it. Wait, what's this is the anode. Anode, cathode. Wait, no, I just did that backwards again. Oh! This is the anode. Cathode. Whew, almost forgot that E, baby. Can't forget the vowels. Okay. So, anode, cathode, reservoir. Obviously H2 outlet, O2 outlet. Okay. So now, now I need to add inlets and outlets for the water itself. For the water itself, which I'll mix, I'll create the solution. Well, for the aqueous solution itself, I shouldn't say the water. I should say the aqueous solution because it's going to consist of salt ions as well as water molecules itself. Yes, because the salt ions are what act as charge carriers in the water. And another thing I need to figure out is the resistivity of water. Surely this is some sort of data online, must be, no? Here we go. Resistivity of salt water. But it's going to depend on the concentration as well. Okay, so first let me figure out the volume. Whoops. Here, gone. Okay, so first thing first is I need to figure out the volume of my reservoir and things like this, because this is what's going to the volume of my reservoir is going to determine the amount of water I can hold in there, and the amount of water I can hold in there is going to determine the amount of salt I can add without what do you call it? Like, it's a concentration thing. It's either oh no. It's dilution. So it's like I don't want to. No, it's not the dilution. I'm just trying to say I don't want to add too much salt to where it's no longer soluble. I have to add a perfect amount of salt that it maintains solubility, because I don't want any salt matter. I don't want any physical salt or solid salt in my water. And especially if I'm going to be using a pump to add and remove the water, I can have no solid matter in there. So that's something that's it's all gonna be determined. The volume of my water is going to determine the concentration of my solution. So, and my concentration is going to depend on how much salt is added in and stuff. And I don't want to be, I don't want to reach that point of man, I cannot remember the word. Okay. Let's continue on. Okay, so this is my reservoir. This is what we got going on here. I need to zoom out. How do I zoom? Here we go. Okay. put that up there. You can still see it. Very good. Voltage divided by the resistance of the water is going to determine our current here. Okay, so now let's look closer to these. So we're going to have some sort of angle on that anode, on the anode. Whoops. And the cathode is going to just be horizontal. Come on, I want the two lines to touch. There. I don't know, whatever. Okay, so we're going to call this angle theta. Theta. And now here's the... We're just going to consider it to be a cylinder. And what I have to take the place of these electrodes are graphite rods. Small graphite rods, which I used in my original design. Right here. Which, this is a great electrolysis reactor. It's fantastic, absolutely. But my new version is going to be much better. It's going to be much better. So, yeah, very simple design. And you can see I have quite a great distance between the two electrodes, which is killing my efficiency, no doubt. Although this thing does produce hydrogen at a fairly decent level. I was surprised to see it. And I was operating it at, I did 12 volts, and then I cranked it up to, what did I turn it to? 21 volts is what I did. No, just 20 volts. It was 20 volts. But anyways, whatever. Minor differences. Obviously, it operated, it had a greater rate of production at 20 volts than it did at 12 volts. So this is all determining. But that's what increasing the voltage also proportionally increased the current. You know, this is the relationship that we're looking at. The resistance can be lowered by a greater concentration of your aqueous solution. If there's more salt, you have more ions. And so the current, electricity can travel, or electrons can travel with lower resistance, right? Because you have a higher concentration of salt water, more salt ions in the water. So this is where we're at. You know, these are things to think about when making a design, when designing. Okay, so here's the one electrode, and we're gonna have some sort of angle between them. And then here's the anode. That's huge. So, and again, this isn't to scale, it's only to understand better of what we have going on here. Okay, so, and then this guy is negative charge, negative. This guy here is going to be positive. Whoops, positive. Just like that. I don't know why that square is going there. But anyways, we got this angle theta, and that's going to determine, so I want to know the distance between the two of these. So how are we going to figure this? I mean, is this so important? I guess if I'm doing a calculation, if I'm looking to calculate certain things like rate of production and efficiency and things like this, then yeah, I'm going to need to know the distance here. But, I guess, you know, we should look to achieve a level of precision. The one thing I've been incapable of doing is, getting my dimensions in my 3D printing, or in my 3D designing software. So getting the dimensions correctly and having them transfer into my Creality slicer software, the software that produces the G code for my 3D printer, right? You have to do this. You have to do this transfer, this export. So one thing I'm incapable of doing is like designing something to specific specifications and then having it transfer consistently and not changing into the Creality slicer software. So if I were able to do that, to get the dimensions correct and to have my prints to print within an accuracy of those dimensions, then I can have accurate calculations, which would be very beautiful. But it's kind of it's unnecessary. But to go through this process will make me a better engineer, undoubtedly, right? Okay, Okay, so... Alright, so I guess let's continue then. Let's continue then. Okay, so I have this here. We're gonna have this angle theta, whatever it is. Yeah, but from this point... You're gonna have an electric field here. Shit. Oh my goodness. Okay, these are my electric field lines. What? I really suck with this pad. Guys, my bad. Okay, so an electric field. You know, I just thought about something. No, I guess it wouldn't still be like that. Okay, never mind, never mind. Okay, so this is what our electric field is going to be like. You know, this is going to be charged Q to some certain amount Q. But I guess at some point we don't have... But the thing is, I guess now that I think about it, we don't have an insulating material between the two electrodes. So it's like maybe, you know, we don't necessarily need to think about this in this manner. It wouldn't be thought of like that. It'd be thought of like this. And the entire volume of the water isn't going to determine the resistivity or resistance, nothing like this, although concentration is kind of dependent upon that. But it's going to be more like this. Let's draw it like this. So we can say that, you know, fuck it. Say this is one electrode. This is our water in between the two electrodes. You can say that he's positive, he's negative, and this is our water, our salt water of a certain concentration. And this salt water is going to act essentially as a resistor. And so now this is going to be the distance that I want to know between the two electrodes, because that's going to determine our resistance of water. Resistivity. Okay, and that's sodium chloride aqueous solution, which means it's been dissolved in water. Okay, so that's essentially what we're going to be looking at. You know, let's look at the system as if we were applying 12 volts. 12 volts. We'll say that. Just 0 volts. I don't know, whatever. I don't need to write that. I guess all that, I mean, I don't know. That's not so important, though. That's not really so important. I don't need to think about that, actually. I don't know. I'm kind of wasting time with that, with thinking about the circuitry of it. The one thing I need to think about is just the geometry so that I can go and begin designing it in the 3D designing software. Okay, so let's get a better understanding of this. So let's get back to what we're doing. Okay, so looking at this here, we're going to need an inlet and outlet for water. I mean, a reason to use a water pump. Let's do it. Let's use a water pump now. And then we're going to have to add a filter in there so that I don't make sure that if there were any salt to not dissolve, that it's not going to get into the pump. It's definitely going to be a much better design to use a pump. I mean, Mm. Or perhaps we should just simplify it, simplify the design. We'll add a reservoir, and we'll just make it so that I just add the water myself. Okay, so let's. Okay. I'm going to start. Can you see that? Yes. I can't get rid of my taskbar. It won't fucking go away. I mean, wouldn't it be better if he was pretty much almost to the bottom of the reservoir? Still kind of going too far. I think that'll work. I mean, these are going to be small channels because I'm not going to be producing much. But if I were to do something like that, I gotta see it from a different angle. So that's my front view. Different angle. But I want that to be all around. So it'd have to be like that. Okay. Okay, so I'm gonna have, thin diameter channels. Actually, let's make, why not make the print somewhat complex? Just for the interest of it. So, I'm trying to think of what else I could do. Okay. I mean, is it me? Like, is it just me that can't draw on this thing? Shit, man, if I was drawing on paper, could actually make it look decent. But that one didn't do it. Okay, so like, you know, like this, and then this will be integrated. Okay, I was like drawing super straight there, but I was trying to go at an angle. Look at how straight I'm drawing. I was trying to go at an angle, man. I'll get it down eventually. That's crazy. I'm not drawing at that crazy of an angle. Yeah. Nice. I love when it doesn't fucking work. Cool. Okay. Okay, buddy. I just gotta do this every fucking time. Bro, why? Why? It's like I can't do it back to back. Of course, now I can down here, but when I'm fucking working up here, I can't do it back to back. Ah, okay. So like this, and then what? He's gonna have a place for the electrodes, but the electrode placement is going to avoid these. These are gonna be here in the same places. You have to avoid these tubes. Oh my gosh, man. That's crazy. And then these are the electrodes. So avoid those. No, I'll have it on top of there. So I'll have, you know, the inlet for water. Huh. And the outlet. Just like that, I guess, right? Alright, that looks great. Okay, you know, I think I got a genuine idea of what I need to do. So, let me go ahead and open up Blender here now. How enraging! Okay, Blender. Oh. Alright, bet, let's begin creating. Let's see how fast I can do this. Oh, you can't see it. Here you go. Alright, now we're ready. Now we're rolling. Let's go. Alright, we're gonna start by adding a cylinder. Get a cylinder up in here. Alright, that's gonna be our reservoir. And again, like, I don't know, I'm not doing anything to exact dimensions. I wish I was, but I ain't got it like that. I ain't got it like that. I could, but I don't care to take the time right now. Yeah, that's exactly what I wanted, bro. That's why I grabbed the blue axis. I mean, shit don't gotta be thick. It doesn't have to be super strong. So let's make it like this. You know, perhaps I don't want to get rid of the top, really. At least not yet, though. So let's just hollow it out. That's great, just like that. Okay, now we're gonna add this Boolean modifier to remove the area which the other cylinder is taking up. Difference. Just like this, apply, and then now, although you can't see it, but we've hollowed out that cylinder here. Okay. Now let's add a cone. I just want to get rid of him. Okay, now this is all going to be dependent upon how big we want to make this. So let's make this take up a good amount of this area. We don't want it to take up all though. Okay, I like it. I like it. That's what we're going with. You know, I guess instead of doing that, because I want it straight, I don't need to angle that. I'm gonna bring him back and then size him to the same as him. Just do that. I mean, yeah. I'm gonna have to figure out more than just this, though. But this is what we want for now. So in order to see that wall, we're gonna click that button there to see how low he needs to go. Right there's good. And again, we'll solidify that. We're gonna add that Boolean modifier. Bada bing, bada boom. We're gonna add the difference here. This time I can see it. My computer's acting very slow. I'm guessing it's because I'm streaming right now. It's having a hard time handling both. Okay, so there. Get rid of him. And now you can see we've hollowed it out. It's kind of hard to see that dimension right now. How our opening hole is a bit smaller than the inside. But oh well, that's fine. Yes, that's fine. That's good. And now I am going to want to use him. But first, I'm going to get rid of some of that too. So, duplicate this. And we're going to do about this, you know, approximately the same thing. So go like this. Don't really want it like that. Yo, what's good?
What's up, chat?
Everybody say hi.
What's up, chat?
Chat says hi. I got like 3 people watching. They say hi. Nuh-uh?
It is.
What's it about? Well, I mean, like, I know what's it about, but is it good?
Yeah. It's really good. One thing I thought of it was the electricity aspect of it.
What about it? What do you think?
In the book. I'm gonna have to read on it.
Hey, that's
Thinking
gonna
of
be
like
cool.
a solar panel. That'd be pretty cool, but that's pretty expensive.
No, it's not.
I guess not.
I guess, but it depends on well, it depend on like, wait, are you gonna have it move automatically, or what's the electricity to run, like a water pump or what?
The heat lamp.
That is kind of a lot of watts.
No.
You could have a, you could have a windmill on it and solar. Were you trying to? Is that the route you're trying to go?
I don't really know. I mean, solar would be cool. A window would be hard. Not for you, but. I don't know, make a window for.
Okay, we're gonna want to add another cylinder. Come here. Now this is kind of going to determine the diameter of my pipe, but I'm not really sure what to do yet. Whatever, I'm just doing all of this. I'm just guessing. I'm fucking winging it. Yeah, something like that. That's good. Boolean difference. Oh. Okay, much better. Okay, so add this cylinder. Now we're gonna make our array of electrode placeholders where our electrodes are gonna sit. We're gonna want to make this at a 90 degree. That's one thing I don't know how to do. I gotta see how that'll work. Oh, okay, yeah, that's what I want to do. I mean, I could just start with 4. That's right, I have to have the wall too. So... So I have to make it bigger. I need it deeper than that. there, something like that. And then here I'm going to need to move these electrode placeholders up so that it's behind that wall. Like that. Just like that. Add more. Okay. Now these ones will be angled. Yes, that's what I want. Maybe I should do more. It's gonna have to be like that. And then what is it going to be like? What, 180 degrees? 95. No. Oh. Or 90. Wait. It was 90 look like. It was 0 look like. Oh, okay. So what? 365 minus 15? 350. Yes, that's what it is. Okay. Alright, cool. Yep. That looks good. Other than that. Hmm. I don't know why those are so much higher than the other ones. I don't know. I don't like it. Yeah, it's better. Okay, so all right, now we're gonna add the modifiers. Him first, apply, apply. Okay, now we can get rid of those. We have our holes for our electrodes. And we can see that wall is still there. This as a separate object, add modifier, generate. Um, okay, let me try this. Let me join all these objects, and then maybe I can just. I think I've done this before, and it doesn't. For whatever reason, it causes a glitch. I'm just gonna do it individually for now. Okay, there. Okay, and then now we have placeholders for our cathodes. No, anodes. Our anodes. That's where the negative electrode will be going. Okay, just like that. I don't know, I'm kind of dissatisfied with certain things, but I'm just gonna roll with it for now. Okay, the other things I need to add are the inlet and outlet for water. So, let's get a cylinder back, not iron. That's a good one. Make them a bit smaller. Yeah, so that's the hole for our water inlet, but I'm going to add a funnel to it. So it just makes more sense. And then, well, right here, that's, 45, 30. Whoops. Bro. Wait. Minus 90. Fuck. Okay, finally. Alright, there it is. I want to live in Calabasas. I just want to live in Calabasas. Alright, yeah, it's looking pretty decent. So now I need the tubes that are going to carry the hydrogen. Or the oxygen, I mean. Alright, zeroed up, zeroed up. I guess, wait, I know what I can do. To make sure this shit's lined up properly. I'm gonna add this cylinder, we're gonna turn it on. Whoops. I think it's this axis. Yes. Yeah, we're just gonna like that way. I gotta make him way smaller. Like that. And now I want to be 45 degrees. No. That's not turning me the right way. Like that. What the fuck am I? Okay, I need it in that plane. Now what if I turn it about here? And there we go. That's what I need. Okay, so 45. Way too fucking big. There. Okay. So, nope, that hole's there. So we're gonna be everywhere. to my boy. Cool. Okay, so yeah, that's good. Okay. I gotta make sure I'm not coming out the bottom. I'm not even touching it. Let's go down. That's good. Add modifier. I don't even know if I'm going to be using this. That's good. Okay, in order to make this easier, I'm just gonna go local. Okay, now it's good. Okay. Okay, first thing is, alright, let's make this one object now. So use that same Boolean modifier, except this time we're gonna do a union. Okay, after that, perfect, apply, get rid of him. And that's good. Okay, I just need to keep, because that's the same one now, so duplicate, size it up. Probably like right there, huh? Actually, I'll have it. Nah, that's good. Okay. Yes, like that. Okay. Just hide him for now. Whoops.
Look, this is what I was talking about doing instead of the brackets.
What? Just
like pocket hole and rotate it like that.
Yeah.
And there's apparently a toenail.
What's that?
What are you gonna do with that hammer and nail?
Yeah, word. Oh yes.
For the vertical. A toenail would look nice.
Okay, and those will be the oxygen outlets right here, and then the main one is the hydrogen outlet. Hmm. I don't know, just thinking about it, it's like I have too much volume. But fuck it, we'll see. That was pretty good. Okay, and this I'm gonna make it a funnel. Do this cone again. What happened to you?
Serious?
What are you doing?
Halloween.
What are you gonna do tonight? You go to work tomorrow?
Yepper
Okay, that's how we're gonna make our funnel. Alright, something like that. I'm gonna have to shrink it. It's way too large. I didn't think about that. So, what, just like this? That's pretty good. I gotta remake that hole. I didn't think about how I'm gonna have to shrink it down and then how things are gonna change. There. Yeah, that's great. That's great. Okay, there. Oh shit, now I'm into that. I don't want to do that though. shit. Nah, whatever, that's good. Okay, boom, and there is our funnel. So it's looking pretty decent, huh? Alright, I mean, well, I don't know. It's the beginning of an electrolysis reactor for sure. Let me cover everything again. These will be the holes for the anodes, and these will be the holes for the cathodes. This will be the funnel to add your solution to the reservoir. Oh my goodness, is it peeking? It is peeking through. Oh no. I gotta move it. How come I can't? Oh, that's what. Global. Local. There. Now it should be good. Is there again a hole? I don't understand what's going on. Is it? How is it at an angle? I'm not sure what's up with that. Whatever. Okay, there. No hole this time. No hole this time. Okay, again, so let's cover it over. These are the holes for our anodes, and these are the holes here for our cathodes. An electric field between the two, or a voltage between the two, will cause a current in the solution, in the ionic solution, which is on the inside of this reservoir here. And through the introduction of the current, it will liberate hydrogen ions and oxygen ions in the water molecules as gases. And respectively, I will collect the gases here in the main. Here in the main compartment, you'll have hydrogen, and then here on the outside compartments, you'll have oxygen. All right, so we'll eventually see this electrolysis reactor come to life physically. I'll print it out, and I'll add the graphite electrodes, I'll wire them, and then, you know, we'll get a good glimpse of what that is like. So, in due time, it is yet to come. Let's you know, I will do my best to remain consistent and actually provide this for you. So thank